The system consists of 3 sections, from left to right: flow control, microfluidic channel, and lock-in detection. Fluid pressure controller can be used to pressurize cells, microbeads, and droplets into the microfluidic channel in a controlled manner. And in the chip, the analyte can create a small change in background current when passing through the sensing electrodes. And this differential current is then precisely detected using the Zurich Instruments HF2LI Lock-in Amplifier. Let's now have a look at the ES technique. It is a label-free technique that enables real-time, high-throughput measurements and ease the process of data extraction and processing. Moreover, ES also allows for multiple parameter analysis and performing several measurements in a single experiment. For instance, probing impedance of the analyte at multiple frequencies simultaneously. It also integrates well with other analysis methods such as optical detection. But despite all these obvious advantages of using ES, 2 challenges remain. First, how to detect fast and weak signal changes in the noisy microfluidic environment, and second, how to interpret the complicated impedance spectroscopy measured. So measuring particles or cell in a microfluidic flow is a good example, as it requires both high sensitivity and fast response. Differential current measurement using a lock-in amplifier here is the key to achieving this sensitivity and speed. This allows us to remove a background signal coming from the microfluidic medium. Just imagine yourself walking from one to another end on a moving bus. The speed of the bus does not really matter. The resulting signal after command mode rejection may still be weak, so we use lock-in detection to selectively amplify it. The HF2LI has a dynamic reserve of 120 dB, which equates to being able to hear a watch ticking next to a jet engine. If you are curious to learn more about this technique, feel free to visit our website and look for our lock-in detection white paper available on www.zurichinstrument.com. In addition, the HF2LI also differs fast measurement speeds and required by microfluidics thanks to the wide bandwidth filter and fast data transfer. So below is a sketch of the ES setup. You see the difference is the current is taken by 2 pairs of sensing electrodes, one with cell and another in pure background. The HF2LI and HF2TA can take care of both signal generation and detection. So let's now have a look at this animation to have a clear understanding. When the cell moves closer to the sensing region, it will modify the electric field between the left electrode pair. In this particular case, let's assume the cell is insulating and no field line can pass through. Hence, the difference of the current measured on both pairs will decrease in amplitude, reaching a trough when the cell is really in the middle. And when the cell moves outside, let's say maybe into the second pair, the signal will be inverted into a peak. And finally, when it moves farther away, we see or we expect the same background as the cell entered before. Please note that even though the signal here looks like a period of sine wave, it is not the raw current. Rather, it has already gone through demodulation.